Electric charges and fields. So in the first page where introduction is given, it tells about the thunderstorm, lightning, and why we see spark or hearing a crackle when we take off synthetic clothes. And it is written that we experience a sensation of electric shock either while opening the door of a car or holding the iron bar of a bus after sliding from a seat, which is due to the discharge of electric charges. Electrostatics is nothing but the study of static charges and deals with the study of forces, fields, and potentials arising from static charges. Next page we have electric charge, which is telling that like charges repel and unlike charges attract, and we see that electric charge is a property of matter which causes it to experience a force when near other objects which are electrically charged objects, positive or negative charge. Like charges and like charges, I already told you, charging by rubbing of insulator causes transfer of charge. They can also be charged by conduction or by induction. Conduction charges the uncharged body with the same kind of charge, but induction charges the uncharged body with the opposite kind of charge it possesses. Suppose it is possessing positive, then it would charge it negative. The property which differentiates two kind of charge is the polarity of charge. Benjamin Franklin, basically, he by convention he named charges as positive and negative charges. Next, in the third page, we have a simple apparatus used to detect the charge in a body is the gold leaf electroscope. It consists of a vertical metal rod housed in a box with two thin gold leaves attached to its bottom end. When a charged object touches the metal knob at the top of the rod, charge flows onto the leaves and they diverge. The degree of divergence is an indicator of the amount of charge. So, what is an indication of the amount of charge? Degree of divergence. Gold leaf electroscope is nothing but a vertical metal rod housed in a box with two thin gold leaves attached to its bottom end. Now let us try to understand why material bodies acquire charges. You know that all matter is made up of atoms or molecules. Although normally the materials are electrically neutral, they do not contain charges, but the charge are exactly balanced. Forces that holds the molecules together, or that holds the atoms together in a solid, are nothing but the adhesive force of glue. Forces associated with surface tension are basically electrical in nature, arising from the forces between charged particles. Thus the electric force is all pervasive and it encompasses almost each and every field associated with a life. It is therefore essential that we learn much more about such a force. To electrify a neutral body, we need to add or remove one kind of charge. Obviously, when we say that a body is charged, we always refer to an excess charge or deficit charge. Okay, in solids, some of the electrons being less tightly bound in an atom are the charge which are transformed from one body to another. A body thus can be positively charged, obviously, by losing some electron, and negatively charged by gaining some electron. When we rub a glass rod with silk, some of the electrons from the rod are transferred to the silk cloth. Thus, the rod gets positively charged and the silk gets negatively charged. No new charge is created because charge can neither be created nor be destroyed. Okay, so yeah, and the number of electrons that are transferred is a very small fraction of the total number of electrons of the material body. Next, we have conductors and insulators. Conductors which allow the electricity to pass through them easily, like the metals. Insulators which do not allow electricity to pass through them easily, like the non-metals. Some substances readily allow passage of electricity through them, others do not. Those which allow the electricity to pass through them easily are called conductors. They have electric charges, electrons, which are comparatively free to move inside the material. Metals, human, animals, bodies, and earth are conductors. Most of the non-metals like the glasses, porcelain, plastic, nylon, wood offer high resistance to the passage of electricity through them. They are called insulators. When some charge is transferred to a conductor, it readily gets distributed over the entire surface of the conductor. In contrast to that, if some charge is put in an insulator, it stays at the same place. This property of the materials tells you why a nylon or a plastic comb gets electrified or on combing hair or on rubbing, but a metal article like spoon does not. The charges on a metal leak through a body to the ground as both are the conductors of electricity. However, if a metal rod with a wooden or a plastic handle is rubbed without touching its metal part, it shows signs of charging. There's a third category called semiconductors, which offers resistance to the movement of charges, which is the intermediate between the conductors and the insulators. You can see the diagram in figure 1.2. We have the metal knob, metal rod, rubber, glass window, gold leaves. Okay, so this is the gold leaf electroscope. Now comes the basic properties of charges. First of all, we have additivity of charges, charge conservation, quantization of charges. Okay, so the first, we have seen that there are two types of charges, positive and negative. If the size of the charge bodies are very small as compared to the distance between them, we treat them as point charges. So when they are treated as point charges, if the size of the charges are very small compared to the distance between them, we term them as point charges. Additivity of the charge. Total charge in a body is the algebraic sum of all the charges located anywhere in the body. Conservation of charge. In an isolated system, total charge always remain conserved. Quantization of charge. Charge can be quantized. Quantization of charge denoted by E. Q is equals to plus minus any. Electric charge is an integral multiple of basic unit of charge. One question to note in the additivity of charges is what is the difference between mass and charge? Mass of a body is always positive, whereas charge can be either positive or a negative. Proper sign should be taken in while adding the charges of a system. Charge is conserved, as I already told you. Sometimes nature creates charged particles. A neutron turns to a proton and an electron. The proton and electron thus created have an equal and opposite charge, and total charge is thus zero before and after the creation. Quantization of charge. All charges are free charges. All free charges are integral multiple of the basic unit of charge denoted by E. So Q is equal to NE. N is any integer and it can be positive or negative. The basic unit of charge, that is an electron or proton, electron minus E and proton plus E. Okay, this the quantization of charge was first suggested by the experimental laws of electrolysis discovered by an English experimentalist Faraday and demonstrated by Millikan in 1912. The SI unit of charge is coulomb, denoted by C. A coulomb is defined in terms of the unit of electric charge, which you are going to learn in the subsequent chapters. Electron, E is 1.6 into 10 power minus 19 coulomb. Thus, there are about 6 into 10 power 18 electrons of charge in minus 1 coulomb. In electrostatic charges of this large magnitude are seldom encountered. Hence, smaller magnitude, that is 1 microcoulomb, which is 10 power minus 6 coulomb, and millicoulomb, which is 10 power minus 3 coulomb. If the protons and electrons, the basic unit of charges in the universe, all the observable charges have to be integral multiples of either. If a body contains n1 electrons and n2 protons, the total amount of charge in a body is n2 into E plus n1 into minus E. So n2 minus n1 into E. As n1 and n2 are integers, the difference is also an integer. So basically, the grainy nature of the charge is lost and appears to be continuous. Okay. Next, we have another topic which is at macroscopic levels. We deal with the charges that are enormous compared to the magnitude of the charge. 1 microcoulomb contains 10 power 13 times the electronic charge. Macroscopic level quantization of charge can be ignored. Now comes example 1.1. जिसमें क्या बोला है, बेसिकली देर आर 10⁹ electrons moving out of the body to another body every second. How much time is required to get a total charge of 1 coulomb on the other body? So we can simply write that Q is equals to Ne and N is equals to what, Q by E. So we know E, and Q is 1, so 1 by 1.6 in 10 power minus 19. And calculating, we get around 198 years, because 10 to the power minus 19, yes, see, 10 to the power 9 electrons move, so 10 power 9 into 6.25, wait, yeah, 6.25 into 10 power 9, because the time required, basically it's 365 days, 24 hours and 3600. Next example, we have how much positive and negative charge is there in a cup of water. So water, which is 18 gram, so it is given in 250 gram of water, let's assume. So given mass by molar mass, so 1 mole has 18 gram into Na, that is the molecules, in 250 by 18 into Na, that is 1.34 into 10 power 7 coulomb. So this is basically I have taught in this lecture. The next lecture would be coming soon. Thank you.